Let's say that we have a parabola with the known point 2, 4, and the slope of 2 when x equals 2. We, however, want to know what f of 2.2 is. To do this, we can approximate using linearization. Linearization uses the tangent line of a point to approximate the value of another point. It's typically useful for points that are extremely close together. In this case, 2 and 2.2 are pretty close to use linear approximation. Let's take the point slope formula y minus y1 equals m times x minus x1. By manipulating this equation, we can substitute in our given variables to come up with the linearization equation y equals f prime of x1 times x minus x1 plus f of x1. After subbing in all the points, we are able to find that the approximation of f of 2.2 is 4.4.
Now it's your turn. Given f of x equals x cubed minus x squared, where f of 2 equals 4 and f prime of 2 equals 8, find f of 1.8. Here's how to use linearization to get an approximation for f of 1.8. Since we know the formula is L of x equals f prime of x1 times x minus x1 plus f of x1, we can plug in the givens. Solving the equation, we end up with L of 1.8 equals 2.4, which is very close to the actual answer of 2.56.
Here is a cubic function with both a relative maximum and minimum at two separate points. To find our relative max or min, we need to see where on the graph the slope is either 0 or undefined. In this case, we only need to consider when it is equal to 0. Let's first look at the relative max. The graph on the left of it has a positive slope that becomes smaller as we reach the relative max. This makes sense since the slope is 0 at the max. Once it passes the max, the slope becomes negative. A positive to negative sign change in the slope will give us a relative max. Likewise, the graph to the left of the minimum has a less negative slope as we reach the minimum.
So let's say that we have a scatter plot of points relating Mr. Liu's stress and the number of trig quizzes he assigns. As you can see by the scatter plot points, Mr. Liu feels less stressed when he gives out more trig quizzes. We will model this correlation with a line y equals ax plus b to figure out which values of a and b will give us the most accurate regression.
To do this, we need to use the MSE, or the mean squared error. Let's call points on the line y hat and the actual points y. To find the MSE, we need to find the sum of all the differences between y and y hat squared. For a line that is totally inaccurate, the MSE will be large. In this case, a horizontal line would give us an MSE of 15. A slightly negative line would give us an MSE of 7. An even more negative line would give us an MSE of 2. Finally, the lowest MSE we're capable of receiving from the scatter plot is 0.1. This is the most accurate line. In conclusion, the smaller the MSE, the more accurate the regression is.
Another way of visualizing gradient descent is by picturing a ball rolling down a 3D graph. This 3D graph depicts MSE against both A and B, the regression variables from before. Let's say the ball is an input, and after rolling down a 3D surface, it falls into a relative minimum of that surface. That relative minimum will have both a corresponding A and B value, which acts as the variables for the best fit.
The speed at which the ball rolls down the gradient is proportional to the slope of the gradient itself. We can figure out the slope with respect to A and B separately. To do this, we will use the linearization formula from before. In the first case, let x be the A variable and y be the output MSE. In the second case, let x be the variable b and y be MSE. Now that we have written out these two formulas, we have an iterative gradient descent in 2 dimensions. In order to find an nth A and b, we can use these formulas. Then, we repeat using these formulas until we reach the bottom of the gradient. As we advance along the gradient, we should expect both f prime a and f prime b to get smaller and eventually approach 0. As they approach 0, the MSE with respect to a and b will approach its lowest value possible. Once it has approached the lowest value, a sub n will approach a sub n minus 1, and b sub n will approach b sub n minus 1. Once they are within an acceptable range, we can confidently say we have found the line of best fit using gradient descent.